Hi, this is Savamanik, analog and mixed signal IC layout engineer. And in today's video, I will explain that how we can design folded Cascode OPAMP in Cadence Virtuoso. In this video, I only discuss the design methodology. In a separate video, I will discuss the theory behind this folded Cascode OPAMP and why we are using that. And this is my lecture number 5. And in this lecture, whatever I will show. So to understand it deeply, please go lecture number 4, lecture number 3, and lecture number 2. Then it will be very helpful for you. Especially lecture number 4 is very vital because in lecture number 4, I explain how we can design Cascode amplifier in Cadence. Therefore, you can see this is also a one type of Cascode amplifier, so it will be helpful for you. So let's begin. Okay, how to solve it. Okay, I hope you can see my screen. Okay, and as I told you that this is a Cascode amplifier, and in lecture number 4, I already demonstrated it. So now what is design? The design is nothing but we need to find the aspect ratio, we need to find the appropriate bias voltage, as well as I will also show you some simulation. Top of that, there is one more portion which is we need to design bias circuit. Whatever bias voltage we will calculate, we need to design a circuit to generate this bias voltage. Okay, so I will make a separate video and explain how we can generate this biasing voltage. But in this video, I only show how to calculate the aspect ratio and how to find the bias voltage. Okay. Okay. So before start in Cadence, we need to keep in mind that this circuit I will explain. But before designing Cadence, we need to keep in mind that we need to keep same length for every match group. We need to keep same length for every match group. What is it? For example, this is a match group. Okay, this is a match group. Let's say the width may be different. Let's say this transistor width is 20 micro, this transistor width is 60 micro, and this transistor total width is 100 micro. Okay, but for a design engineer, you should understand that what will go in the layout. I mean, whenever goes to the physical design, we need to design the circuit such a way that it also helpful for the layout engineer for better layout performance. Okay, for that, what we can do, we can make a unit width. Let's say I take unit width is 20 micro, so I should use 20 micro width for all of the transistor. But the number of finger may be different. Let's say here we can use number of finger 1, here we can use number of finger 3, and unit width is 20 micro, so 3 into 20, the total width 60, it match. And here I also can use 20 micro. You can see the NW is 20 micro for each one, and length 22 is same for each one. Only the number of figure only different. Okay, so we need to keep in mind this thing. Okay, so for our circuit, what is the match group? We can see I already write here what is the match group. So you can see the circuit and you can actually understand what is our match group here. For example, PM3, PM4, you know, it's the differential pair. So this is our match group. Also, there's also some other match group. Okay. And yeah, as I already told you, please watch 2, 3, 4 lecture number. And in this lecture, I already explained that how we can keep a transistor in saturation and how this two curve, VGS versus ID and VDS versus ID, helps us. These two curves help us to keep a transistor saturation, to find the biasing voltage. Let's say you need 300 microampere current. So how you can find? Without calculation, you can find how much gate voltage you need by help of the first curve. So whenever you find the gate voltage without any calculation, only by help of simulation, you can find what should be the drain voltage to keep transistor in saturation. Also, there are also some formula, some basic principles which I already explained in lecture number 1. So if you are new, please watch my previous video. It helps you to understand this lecture very well. Okay, now let's begin a real-time design in Cadence. So before going Cadence, let's understand some basic principle here. I will want to use VDD to 1.8 volt, and the first PM02, this is my tail current. So IT, whatever current generating IT, this current is equally split PM3 and PM4. For example, if IT is 400 microampere, my PM3 is 200, my PM4 will 200. Mean my I4 and I3, it carry 200. Mean this current equally split in two branch. Okay, this point we need to keep in mind. And one more point, that the bottom transistor N5, just consider the half circuit, okay? Because you know the circuit is symmetrical. Just consider one branch, mean PM5, PM7, N2, and N5. So PM5, PM7, and N2, this and N5, these all are in series, right? So same current flow through PM5, PM7, N2. But in N5 transistor, you can see my I3 current also adding in this branch. So the current I5 is nothing but I2. You know, I2 is same, I2, which is flowing PM7, PM5, and N2, same current flow I2 plus the current flowing through the PM3, or we can say it I3. Okay, so this equation or relationship I wrote there, so you can take note, and I hope you easily understand it. Okay, and there is also some design methodology. Let's say my V out, I assume it minimum is my design principle. Let's say 1.2 volt. You can choose any different voltage. You can choose 1.1 volt, you can choose 800 milliampere, you can choose 1.3 volt, and whatever you will pick, you need to design the circuit such a way. Okay, for here, for time being, let's say my V out max should be 1.2, or minimum is 1.2 or 1.3, something like that. And VDD is 1.8, and here I will use 19 nanometer CMOS process. My gain I expect greater than 45 degrees, excuse me, greater than 45 degree, as it is a single stage. It is a single stage. So I might not get around 45 to 50 degree, 50 dB from this circuit. Okay, in obviously we can add a second stage, but not now here. So in from there, from this first stage Cascode OPAMP, I may get more than 40 degree or around 45 degree dB gain, but my phase margin should be greater than 60 degree. Is good, you know, and I assume my power is 1 milliwatt, but for the phase margin it should be greater than 45 degree to avoid oscillation. Or I will make a separate video where I explain the relationship between frequency and the phase margin, that it will better for you. Okay, and here I will use gain 2 micrometer, and my 3 dB bandwidth should be 5 kilohertz or more than. Let's see from the design. Okay, I already explained this thing to you. So okay, so here whatever we'll do, we just consider the half circuit. So here we also take some sub-circuit to help to design the circuit. But first of all, this is formula number 1. In step 1, we need to calculate the overdrive voltage of a single branch. In the folded cascode path, if consider the half circuit, we need to calculate what is the overdrive voltage of each transistor. How can we calculate? We can calculate it by using this formula. You can see. So I do not think that we need to explain it. It's just a straightforward formula. And yeah, and you know the VDD is 1.9 is calculated. So we find all of the overdrive voltage. The sum of all of the overdrive voltage is 1.2. Mean PM5, PM7, N2, and N5. The overdrive voltage of all transistors is 1.2 in this case. Okay. Okay. But one more point. My V out is 1.2. So we need to design N2 and N3 such a way that my N2 and N5 in saturation. Please go lecture number 4 for the Cascode amplifier. I explained it very well. And please be remember my Vx. My Vx should be such like my N5, the bottom NMOS should be in saturation, as well as my PMOS PM3 should be in saturation. You know the basic relationship for saturation, or go lecture number 1. I always referring previous lectures because I explain it very well. Okay, this is the basic principle you should to keep in mind. Okay, or my V out mean, which we took 1.2. This 1.2 mean my VD set for N2 or my VD set for N5. The summation of this two VD set should be 1.2 or less than 1.2. If it is greater than 1.2, then this two transistor will not in saturation. This is the condition. Okay. Okay, this is some hints. Let's see why we say this is a cascode amplifier. So what is cascoding? I explained it in my lecture number 4. I repeat it here. So N2 here, it is in common gate configuration. So in common gate, if my Vx increase, my Vout will increase. If my Vx decrease, my Vout will decrease. Why I mention it here? It helps you to play with the circuit. It helps you to play with the circuit. Okay. And my BG3 should be greater than BG4, and my BG1 should be greater than BG2. Okay, I wrote an explanation here. If you have any question, please comment. Okay, I'm going in step 2. In step 2, we need to find the overdrive voltage. In step 1, we find that the summation of overdrive voltage is 1.2. So we need to now calculate this overdrive voltage, right? To calculate this overdrive voltage, we need to understand one concept. The concept is the mu p, the mobility of PMOS is smaller than mobility of NMOS. And we can also see this from DC analysis. If you just make a circuit like this for PMOS or for NMOS like this in diode connected configuration, and you can pick a current. Here I choose 300 microampere current. I will explain later why I pick 300 microampere current. But if you make a circuit like this, then you just run a DC simulation, and from DC simulation you find the mu p, the threshold voltage, the transconductance, everything. I already explained in lecture number 4. So please go there. So here I pick width equals to 10 micro, or you can choose any width, but length should be 2 micro, whatever we pick. And why we make it diode connected? We need to ensure this transistor in saturation. Therefore, we make it diode connected. So let's say from here, if we go direct print, print this operating point, so we can find the mobility of any circuit. Okay, for the mobility, you can see there is a term beta effective. So what is beta effective? We need this value, beta effective. Okay. Okay. 300, 100, you can see this. So I explain later how I choose the current, why it is 300, why it is 100. I will explain later. But for now, I run several simulation for 100, for 300, and I find the mobility every time to check how mobility changed, nothing else. Okay, and here I use W by L is equal to 5, W10, L2. Okay, so what is beta effective? Beta effective is mu CUX W by L. This is the formula. Let's say if my beta effective is, 1 milli, Then how we can calculate mu and Cx? We already know W by L. In my case, it is 5. In your case, it may be different. So we need to just divide 1 milli divided by 5. Then we can find the mu n. And it is PMOS, then we can find the mu p CUF, right? So we to pick a mu p and mu n value. Okay. Okay. Here I explain you. If you see, if I change the for NMOS, let's say if I change the current, the mu n value will change, right? So you don't need to worry about that. You can pick a single current, and for a single current for NMOS and PMOS both, you will need to find one mu n on one mu p, and we will use this one mu n, one mu p for all of our calculation. We don't need to consider 298 and 176. We don't need to consider different mu n. We need to consider one single mu n, and for all of our calculation. Okay, and from here we can also find the threshold voltage, and we can see the threshold voltage will not change too much drastically. Okay, I also wrote this point here. Okay, the best way design I take 300 micro and find the mu n and mu p for both cases, and I use it in all of our calculation. Okay, okay. One more point we need to understand here. One more point. The point is, sorry for every time it's changing. Okay, okay. The point is that, so we see the mu p is smaller than mu n. So let's say in the circuit, this is my actual circuit, whatever I'm using. And I already told that this branch, let's say this branch is carrying, for example, if 100 microampere current, this PMOS also carrying 100 microampere current, this NMOS also carrying 100 microampere current. But as the mu p, sorry, but as mu p is smaller than mu n, so we need higher overdrive voltage for PMOS compared to NMOS. It's clear? I also wrote it here, so you can see it from here. Okay, or the formula. What is the overdrive voltage? Overdrive voltage is nothing but VGS minus VTH. So from this formula, we can also see if my mu and CUX increase, VD decrease. Okay, the formula is inversely proportional. Also, there's a rotobar. Okay, but the inverse relationship. Okay, so as my PMOS has lower mu value, so it OD will increase. Okay, I hope it's crystal clear. So what we know? We know that my summation of all overdrive voltage should be 1.2. Okay, so from there, we need to divide this 1.2 volt in all of the transistor, Okay, so we can assume, it's just my assumption. I assume for PMOS, PM5 and PM7, the overdrive voltage is 350 millivolt for each. So, okay, so I take 350 millivolt, and you can see it is higher than the NMOS. Okay, so if I take here 350 millivolt, so for 2 PMOS there is 700 millivolt, and we left 500 millivolt left. Okay, so we need to now split this 500 millivolt between N2 and N5. And one more point, as my N5 carrying more current, I already explained, the bottom NMOS is carrying higher current compared to N2. So N5 also need higher overdrive voltage compared to N2. So for in this case, I assume my overdrive voltage for ODN is 300 millivolt, and overdrive voltage for OD2, mean the ODN2 is 200 millivolt. And if you sum, it will be 1.2 volt. The total will be 1.2 volt, whatever you calculated in step 1. And from the formula, we can see the relationship between ID and overdrive voltage is proportional. It means if ID increase, my OD will increase. So as N5 carrying higher current, its OD should be higher compared to N2. Okay. So now we need to find the current. we need to find the current. Which current? The current flowing through this branch, this cascode branch, and current flow through this differential branch. We need to calculate it. How we can calculate it? Okay, we can calculate it from the power. So we assume here power is 1 milliwatt. So what is PT prime? PT prime is nothing but the total the total current mean, sorry, not PT prime, is IT prime. What is IT prime? IT prime is the total current flow through the circuit. So what is the total current? The total current is I5 and I4. Let's see from here. What is the total current? For the total current, we need to consider the entire circuit, not the half circuit. If you consider the half circuit, the total current is what? I5. And for the another branch, we can see there is one more current, I4N, and I5N and I4N is identical. So we can say the total current is twice I5. Okay. If we consider half circuit, so we can say the total current should be twice I5. It's clear? So here we are considering the entire circuit, not the half circuit. Okay, the entire circuit. So we need to consider two current. Okay, the both current for the two branch. Okay, so in this way, from this formula, we can calculate that my I5 should be 277 around microampere. Okay, so for the design purpose, I assume it is 300 microampere current. My I5. Okay, so and the it's symmetrical. The two branch is same current, two branches same current. Okay, so now consider the half circuit. Okay, so now 300 microampere current through my N5, right? So what is the N5? As I explained you, the N5, the current through the N5 is nothing but current coming from the differential path and current coming from the folded cascode path. The current coming from the folded cascode path. Okay, the current flow through this transistor N5 is nothing but come from this top side and coming from this folded cascode path, and this current is sum of summation. The summation I already explained, right? Okay. Okay, now we need to split this current. We know the current is 300 microampere, so we need to design a circuit. The total current is 300 microampere. So I will design the differential pair such like that it will provide 200 microampere, and I will design the top PMOS, PM5, PM7, and NMOS, and 2 such like that it can carry 100 microampere. So my total current in N5 is 300 microampere. Now you can ask me that why I allocate 200 microampere current for the differential pair and why I allocate 100 microampere current for the cascode path. It's my intention. It's you can also assume a different value. Why I increase higher current in this differential path? Because the gain of the circuit related to the GM of the input stage, the GM of the input stage for up circuit, let's say PM3, GM of PM3, and this is one of the formula of GM, and we can see if my ID increase, if my current increase, my GM increase, eventually my gain will increase. So this is my intention. So if I assume higher current in this branch through the PM3, it's mean its GM will increase, my gain will increase. Okay. So now we know the current in this branch, we know the current in this branch, and we also know current flow through the PM0. Why? How we know? As I already explained that the PM3 and PM4, this current is equal, and this current is nothing but the total current PM0. So if it is 200 micro and PM4 also carrying 200 micro, obviously PM0 will be 400 micro, half of this, okay? Double of 200, double. It's simple, right? Okay. So if you understand this, so now this very simple. Now this step is very simple. Now we should design we just need to find the W by L ratio. That's it, nothing else. And For calculation purpose, we assume there is no channel length modulation factor, lambda equals to 0. As we are assuming lambda equal to 0, so whatever we will calculate, nothing will be 100% accurate, but we'll find a estimation, and our estimation will be around 85 to 90% correct. There will be 10% mismatch, and we need to twin the circuit. We need to play with the circuit to match it 100% perfectly, to match with the circuit to achieve our design goal. And to play with the circuit, you need to know what goes on here, which parameter we are changing, why you are changing. For example, I tell you this NM2 is a common gate configuration. So let's say if I told you this voltage is Vx. If Vx increase, Vout will increase. If Vx decrease, Vout will decrease. So you need to know the relationship between the circuit. Okay. Okay. So how we can design is very simple. We just use a formula. This is the formula of current in saturation. Half mu n or mu p cox w by L, or overdrive voltage, or VGS means VTH whole square. And we already allocate the V overdrive voltage. We already find the mu p from this type of simulation. We already find the mu p and mu n. You don't need to take multiple, for example, 400 micro, 200 micro, don't need it. Just put one single current, just run it, find the mu p from beta effective and use it for all of the circuit. Same for the NMOS. Okay, pick a random width, pick a random L, and make sure the width and NMOS and PMOS you pick is same. Okay, here I also with 10, here I also with this 10, length is 10. Okay, run a DC simulation, find beta effective. From beta effective, you need to calculate the mu n and use this mu n for all of the circuit. Here I use 300 microampere current. Here I use 300 microampere current, and whatever I calculate, I use it just here. Okay, so from this way, we can find the W by L ratio. So here, if we use mu p equals to 115.4, you will find that W by L is 28.31. Okay, and L equal to 2, so we need to just multiply this value with 2. If you multiply it with 2, you will find 56.62. This is same for everything. So you can pause my video and you can watch it. Okay. One more point I'm illustrating here for the tail current. For the tail current mean this. For PM0, I assume my overdrive voltage is 700 millivolt. Okay. I assume it is 700 millivolt. Why? I know if my VOD increase, my width, length is same, mu and mu p, everything is same. So if my VOD will increase, my width will decrease. If my width decrease, my R out will increase. And this working like a tail current source, And what is the property of a current source? It has higher output resistance. So if we can reduce the width, then the output resistance will increase. So this is our intention. To increase the R out. Therefore, I use here higher V overdrive. Okay, and same calculation, same formula, and I write it. I use 115.4 for everything, and L is 2, so you can easily calculate the width. So in this way, I designed the calculation. So you can pause it and you can write and calculate by yourself. So everything for the NMOS, I use mu and CVX 268.6. All of the NMOS use mu and CVX 268.6 micro, and you will find this parameter, and just 18.6 multiplied 2, then you will find this NM2. Okay, and please be remember the both side is identical. You can pause my video and see. Okay, so now we need to design the bias voltage. Okay, this is the circuit. Every branch is identical, mean it is 36.6, it is also 36.6. So if we design the half circuit, so just copy it over there. Okay, Then now we need to calculate this bias voltages, this bias voltage. So understand this formula very well, how we calculate it. Okay, so let's see from here. So what is VUD? VUD is nothing but VGS minus VTH. So we already assume the VUD for every transistor. For PMOS, it is 350 millivolt. For the NMOS, one of NMOS, it is 300 millivolt. For this NMOS, it is 300 millivolt. For this NMOS, it is 200 millivolt. For this PMOS, it is 350 millivolt. For this PMOS also, I assume 350 millivolt. And for this PMOS, the tail source, we assume 700 millivolts. So we know everything, right? So we need to find the threshold voltage. Notice this formula. We need to find VGS. What is VGS? VGS is nothing but overdrive plus threshold voltage. Okay. Okay. And how can we find the threshold voltage? It's very simple. I already show you that if you run the DC simulation, or you can find also it from this circuit, or you also find it from any of the circuit. Okay. And if let's say you can find it from this circuit. Okay, so if you find the BT for NMOS, BT for PMOS, use it for all of the calculation. For simplicity, use it for all of the simulation, and you will find the VG0, VG4, VG3, VG2, everything you will find it from here. This is VG1, VG2, VG3, VG4. I think it is very crystal clear. Okay. Okay, you can pause my video and see the calculation. Okay, now whatever you wrote here, VG0, VG4, VG3, VG2, VG1, it is it is my VGS. You can see from here, I my overdrive voltage plus threshold voltage, overdrive plus threshold voltage, whatever we calculate here. Let's say for VG0, we calculate 850 millivolt. It is my VGS0. Understand? It is my VGS0. It you can say this is VG4, overdrive plus threshold voltage, overdrive plus threshold voltage. It is my VGS4. It is my GS4. It's mean, for example, VG0. It's mean that the difference between gate voltage and source voltage is 850 millivolt. It should be minimum 850 millivolt, or it may be. Let's see what I used in design. But from here we'll get an idea. Now, this portion is very important. Now we need to find the accurate gate voltage. We know the VGS from here. Now we need to find the accurate gate voltage. How we can calculate it? How we can calculate accurate VGS? Which is VG1, VG2, VG3, VG4. And I already explained this circuit. And I also explain this portion later. First, watch the theory. Okay. Let's start from here. Let's say PM3, or start from PM0. Okay. What should be my VG, gate voltage for PM0? My VG should be such like PM0 in saturation. So from the saturation condition, what is the condition? From the condition, we know that my overdrive voltage plus threshold voltage. Just simply, it's a formula, right? It's a formula. Here, my VG should be PM0. VG should be the overdrive voltage of PM0. I am telling you again, the VG gate voltage for the PM0 is nothing but the overdrive voltage of PM0 plus its threshold voltage. Okay, so from here you can find the VG. It's around 850 millivolt. Okay, so now you need to calculate the PM3. For PM3, what should be my V1, or in the biasing voltage for PM3? Okay, my V1 should be such like PM0 also in saturation, PM3 also in saturation. So how we can meet this criteria? It is very simple. Always remember, always remember, if it is like a cascode structure. If you see any structure like this, mean drain connected to source. Drain, one of transistor drain is connected to source. If you see a structure like this, and you need to, if you want to find the V1 for this type of structure, it is very simple. The overdrive voltage of PM0. Take the overdrive voltage of PM0 plus take the overdrive voltage of PM3 plus the threshold voltage of itself, mean PM3. Understand? The overdrive voltage of top transistor PM0 plus the overdrive voltage itself PM3 plus the threshold voltage of PM3. We need to summation these three. Then we need to minus this VDD minus PM0 plus PM overdrive of PM3 plus threshold voltage of PM3. I wrote it here. You can see VDD minus overdrive voltage of PM0 plus overdrive voltage 3 plus threshold voltage. If you minus this from here, so you can find it is around 600 or 602 millivolt. Okay. So in this way, you also need to find PM5 and PM7. Now you should find the BG1 for PM5. What is BG1? It's nothing but VDD, minus overdrive voltage of VDD minus the overdrive voltage of PM5 plus its threshold voltage. Okay, the overdrive voltage of where? VDD minus the overdrive voltage of PM5 plus its threshold voltage. So we can find it is around 1.3. So what is BG2 for PM7? It's same like the input stage, right? This is same. So VDD minus the overdrive PM5 plus the threshold voltage of PM7 plus overdrive of PM7. Then you can calculate the VG2. Then you can calculate the VG2. The same thing, and the same case also for NMOS. What is the VG4? What is the VG4? VG4 is nothing but the overdrive voltage. The overdrive voltage of top transistor N2, the overdrive voltage of top transistor N2 plus the overdrive voltage of N5. You can see the formula here, the overdrive voltage of N5. Sorry. VG4, let's see where it is. Okay, sorry. For here, for N5, we don't need to consider about the VG3. For N5, just consider the drain voltage of N5. Okay, for N5 it's easy. Just overdrive voltage of N5, the overdrive voltage of N5 plus its threshold voltage, like PM0. The overdrive voltage of N5 plus its threshold voltage. This is BG4. But BG3 is critical. For BG3, we need to consider the bottom transistor also. For BG3, what is it? It is for BG3, it should be the overdrive voltage of N2, the threshold voltage of N2 plus the overdrive voltage of N5. Okay. So in this way, you can estimate this value. So, or you can pause my video and you can see the calculation here. Then how I find this? The threshold voltage is something, everything I took from the simulation, as I was explaining. And now, what is our gain? So, okay, let's activate. Now, what is our gain? Okay, let's see from the circuit. Okay, in my tutorial number 2, I believe I explained, or tutorial number 1 and tutorial number 2, I explained small signal model, I explained cascode structure like this, and how we can calculate gain, everything here. So based on our previous knowledge, we just apply it here. We just apply it here. Okay. So this is my output node, or this is my output node. Please watch my previous lecture if you have any hesitation to understand it. Based on my previous lecture, from output node, we need to see down, we need to see up. If we goes up, uh, up mean the output resistance of PM5 and PM7, and we need to find the output resistance of N2 and N5. Okay. If we go up, we can see PM7 and PM5, right? So the R up is GM7, RO7, RO5. What is RO? I already explained it, so I don't want to long the theory here too much. So please my previous video, but I am explaining here. It is GM7, RO7, RO5. If I go down, it is GM2. The first transistor is, we need to calculate the GM of first transistor. Here my first transistor is N2. So if I go down, R down is my GM2, RO2, RO, N2, RO for this N2 transistor. Then we can see there is parallel. In small signal model, as PM0 providing a constant current, so we can consider this node a AC ground. So PM3 is source is connected to ground, and N5 its source also connected to ground. It's mean PM3, the resistance of PM3 or R, we can see RPM3, the resistance of RPM3 and the resistance of N5 comes in parallel. So what is the down? Our down is my GM N2, GM of N2, RO N2, RO for N2, then parallel RO N5 and RO PM3. It's clear? I already write it here. Okay. What is our up? What is the down? Okay. Okay. Now, how we can calculate that this formula is correct? And what is the gain? Gain is minus GM1 or out. And what is minus GM1? GM1 mean the gain of the input stage. Here, what is my input? Considering for half circuit, my input is PM3. So it should be GM of PM3, right? It's not GM1, it should be GM of PM3. Okay. Okay. So now you can find this GM, RO, ROP for everything. So you can find this parameter from Cadence and you can just calculate the gain here. I am not showing any calculation for gain here, but for example, whatever you calculate here, it is 1350. This 1350 will be your DC gain. How you can convert it to dV? Just log this value and multiply with 20. And I will also explain how we can find GM7, RO7, ROP, everything in my previous lecture, lecture number 4. So go my previous lecture and watch it. Then you can understand this principle very well. But here I just take an example. Let's say if this calculation comes the result 1500, sorry, 1350, then how you can convert it in dV? Okay, now go to the simulation. I am also showing here how you can find it. Let's say I'm showing one example, N5. So if I run the DC simulation, okay, if I run the DC simulation and if I see where it is, excuse me, just give me a moment. There's on print disappearing. Let's see if I see NM5, then what you can see, we can find everything here. We can find R on, we can find R out, right? Whatever I explained there, R out, this is my R out. So you should to pick this value. And if you need GM, let's say we need GM of this transistor, NM2, right? So just select this and you will find the GM of this transistor from here, and you can calculate it by your hand calculation. Okay, so now let's check. What is my assumption? My assumption, this transistor should be carry 400 microampere current. Let's see its ID. You can see its ID, sorry, PM0. The ID for PM0, where it is, you can see it's around 400 microampere, around 400 microampere, right? And uh, the current flowing through this branch should be 200, right? Or nearly 200. So you can see it is, where is my ID? You can see it is 200 microampere. And what is my assumption? This, what is this current flowing through this branch? And to this current, our assumption is 100 micro. So let's see, it's 100 micro or not. You can see it is around 100 microampere, 105. It's around 100 micro. So you can assume this current, what is it? It is summation of these two current. So it should be more than 300, right? Little bit higher than 300 in my this case. You can see it is 305 micro. It is 305 microampere. So, okay. Now, whenever we calculate, find everything from our calculation, and I just design the half circuit. This is the exact value, exact WL value, whatever I find here from my calculation, and this is the exact value of the gate voltage from here. Okay, so from here, I find that some transistors are not in saturation. As I explained, we are not calculating the lambda value, and we are using the same mu n and mu p value for simplicity for everything. So we need to just twin the circuit to match the formula. Okay, so how can we twin the circuit? For this, we need to just know. Please watch my previous lecture. Here I explain how we can keep a transistor in saturation. Plus, you should also know the basic formula of saturation. For example, for NMOS, what is the formula? The formula is my gate voltage should be higher than its threshold voltage. My transistor will on, and the drain voltage, my VDH, should be greater than or equal to its VGS minus TH. You already know this, right? Or you can watch my previous video for more clarification. Then this transistor will be in saturation. If it meets this condition, this will grow in saturation. So in this way, I just twin this gate voltage and make it such a way that it goes in saturation. How I do that? For this, I only design these two NMOS. First, I design these two NMOS, NM2 and NM5. How I design it? I design it here. I know this is my output. My output should be around 1.2 volt, right? Output, you can see it is 1.3 or 1.32, or what I assume it should be minimum 1.2. So for here, I calculate my VDC 1.32, or I find you can use here for initial simulation 1.2. And for 1.2, this is my drain voltage. And from our calculation, you see it is around 476. So I use the same value here. I use the same value here, and I just need to twin the VG3 such a way that it will be in saturation. So here I use VG3. You can see my this value. I use VG3 equals to 1 volt. I use VG3 equals to 1 volt. What is in my calculation? What my calculation says? My VG3, it's 677. So I just twin the circuit. How I twin? I just take the help of IV curves. I watch how we can play with the circuit in my lecture number 4, especially when I designed Cascode OPAMP. In this video, you can saw that we can take help of IV curve, and from IV curve, this curve will tell us what should be my gate voltage to keep both transistors in saturation. So we need to we don't need to worry about that. This curve will tell us when this transistor goes in saturation. And from this curve, I find that when this voltage is 1 volt or greater than 1 volt, this transistor in saturation. And keep in mind, in this case, it is saturation, okay? But in real-time circuit, you can see there is also connected a PMOS, the diff pair here, the folded cascode path here. So you need to design BG3. And when you design the BG3, you also needs to keep in mind that your this transistor should be in saturation. Okay, it's not too much critical. Uh, just run. You can just change this value. Just you need to run a DC sweep. You need to change this value using DC sweep, and you can plot the drain current of NM2, you can plot the drain current of NM5. So if you vary the VG and if you saw the drain current, then you can easily see that when it reaches its saturation condition. And you also can plot the drain current of PM3. You can see its saturation or not. I demonstrated this small thing in my previous lecture, so I am not showing it here. Okay, so in this way, I first these two branch. And after designing this, I design VG1 and VG2 such a way that it is in saturation. And I also slightly twin its width. Might be I play with this width little bit. You can see that here I use 36.6. I think it is same whatever we calculated. Let's see, I forget. What was our calculation? Change or not? Let's see. Just a second, I'm checking. This is the diff pair. I use same value for diff pair. Whatever I find here, you can see. I use their same value for diff pair. For the tail current, what I find, same value, 28.3. I also use here 28.3. You can see I just play with the BG0. I don't change this aspect ratio. I use whatever I find in calculation. For N5, what we find? 49.6 micro, right? 49.6. Let's see. This is my N5. It is 49.6 micro. Then N2, what is this? 37.2. From our expectation, it is 37.2. What is it? 37.2. We can see same value. And for PM7, we use 33 micro. Okay. Just give me a moment, please. Okay, it's little bit higher. It is 33, it's little bit higher, whatever we calculating here, okay? So from my calculation, it should be little bit higher from 28 micro. So our design is 33 micro. How I find this value? I just little bit play with the circuit, little bit change the value and see how we can keep this transistor in saturation, how we can take this transistor in saturation. Okay. Please keep in mind, my all transistors should be in saturation. And what is for PM5? What was our calculation for PM5? For PM5 and PM0, as we assume here, same value. Let's say for 33 micro, same 33 micro. Initially, I picked 33 micro for PM5 because my ID is same, my overdrive, whatever we assume is same here. So if I calculate it using this MUPC-UX 115.4, I will find 33 micro, sorry, 14.14, this value here, okay? But from my experience, from my intuition, for the analog circuit designer, everything will not match whatever you calculated. So you need to little bit play with the circuit. So I see, please keep in mind, if you find this type of structure, always the top transistor should be little bit higher width the width of the top transistor should be little bit higher compared to bottom. Also, the gate voltage of the top PMOS should be little bit higher compared to VG2. Or let's say if my VG1 is 2 volt, let's say if my VG1 is 2 volt, my VG2 should be less than 2 volt. So this is my intention. So whenever I play with the circuit, I maintain this rule. Let's say I use VG1 2 volt. So I never apply 2.2 volt in VG2. I applied, let's say 1.5, I will apply 1.8, but it should be less than whatever I applied in VG1. Or we can just run the IB, we can just run the DC sweep, and we can see what should be my value. From the IB curve, we can find this value. Uh, which value? The gate voltage of VG1 and VG2. Okay. And yeah, and whenever you design these two transistors, we need to make sure that this both PMOS in saturation, whenever the output voltage is 1.2 volt. You can see for this, I take help of this circuit, VG1, VG2, I applied a DC voltage here. You can also apply 1.2 volt, and you should adjust the width of these two circuits such a way, or the VG1 and VG2 such a way, this transistor in saturation. Then you can fit it here. Okay. And so let's see. Here, here, my VDD is 1.2 volt, my VG is 940 millivolt, VG is 940 millivolt. So what was my calculation for it? See, from our calculation, we find this VG0 850, but in simulation, we find that whenever I use little bit higher, then we this transistor in saturation. We should keep in saturation. For the input, here I use 612.46 millivolt, or you can use 612 millivolt. And what was our calculation here? Is 601. It's almost same, little bit change, but it's almost same. As I explained, it will not match 100%. Let's say for VG2, you can see it's 950 millivolt or 952. For in here, what is VG2? VG1 is 1.35. As I explained to you, VG2 should be less than 1.35, and it is 1 volt here. This voltage is 1.32. This voltage is 1 volt. And yeah, that's it. Here from calculation, we can also see my VG1 is higher than my VG2. VG1 is higher than my VG2. So if I use it 1.35, so if I increase this voltage, I also increase this voltage to make a point this transistor in saturation. I hope you understand whatever I want to make point here. Okay, so now we can find the gain of the circuit. Okay, you can just, I just run an AC analysis here, and if I try to see the gain of the circuit, mm, we need to just select the output node and what? My input node. Then we can see the gain of the circuit. So what we can see, the gain is around 30 dB. It should be, there might be some wrong. I also simulated this circuit couple of days ago. Whenever I make this tutorial, whenever I make this circuit for tutorial, at that time gain was around 46. Okay, in further I maybe change anything, therefore this gain decrease. What should be the issue? There is no issue. Okay, there is no connection with the circuit. Okay, okay, whatever gain we find here, let's check the what we applied here. We applied Let's see if we apply 1 kilohertz. Is okay, whatever we gain get here, then you can play with the circuit and you can increase the gain. How you can increase the gain? You can increase the, if you play with the circuit, you can increase the GM of this circuit, right? From formula, what you can see, from formula, we can see if we can increase the GM of input stage, our gain will increase, or you can increase this RO, RO5, the RO value. How can you increase the RO value? It's simple. Let's say here I use L equal to 2 micro. You can also use L equals to 4 micro or L equals to 5 micro. And for this, you need to redo the all calculation. You need to find the VT, you need to find the mu P, everything, and then you can design the circuit in your own way. And I believe if you use higher length, channel length, then you, whatever you, what will happen if you increase the length, the R out will increase. If my R out will increase, from formula we can see our gain should be increased eventually. Okay, so that's for now. Or let's check the gain here also again. Let's see gain and phase. Around V1. Okay, it's 30 dB, but I don't know what it changed here. Uh, so initially when I designed the circuit, the gain was 46 dB. Okay. Okay, so let's check the other parameter from here. So what is my 3 dB gain? My 3 dB gain is 30. So 30 minus 3 is 27. So whenever the circuit is in 27, so here we can see my 3 dB gain frequency is around 5.7 megahertz. It's really very good, really very good. And what is my phase margin here? For phase margin, you need to find where gain is 0 dB. So where it is around 0 dB. So we can see that it is 51, let's say 52 degree. Okay, so whatever we find here, we need to minus it from 180. Let's say 180 minus 52, 180 minus 52. So whatever we will find, it is the phase margin and it meets the condition. Okay, that's for now. I hope this video will helpful you, at least give you the basic understanding how to design this circuit in Cadence. So if you like my video, please subscribe and share with your friend. And I have also a separate popular video how to design two-stage amplifier in Cadence. And you also can watch this video, and you can also watch my previous lectures. That will helpful for you to understand the basic circuit. Okay, bye for now from Canada, British Columbia.